I welcome you again to the UNU-INWEH public event, the Science Talk. For those joining us for the first time, you are welcome. We are very happy you can make it today. Thank you. I am your host, Professor Grace Oluwasonya. Before presenting our distinguished speaker, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions. Please type your questions or comments in the Q&A chat box, and we will pick them up from there at that time. Thank you. I also want to let you know that our previous science talks can be viewed on demand on our YouTube channel, available at unu.edu/INWEH/science talk. Again, you can find our previous science talks on demand on our YouTube channel at unu.edu/INWEH/science talk. The topic of today's talk is simultaneous hydroclimatic processes and extremes with stochastic models. Really, we want to introduce you to what we call cosmos. But I won't tell you what cosmos means. I will leave that to our speaker to demystify. So let's talk. Our presenter is Dr. Simon Michael Papalexiou. I hope I got that correctly, but I'll keep it short, okay? Simon. All right. Simon's research centers on hydroclimatic variability and extremes, the development of advanced space-time stochastic models, downscaling methodologies, and climate change diagnostics. Simon leads the development of Cosmos, a widely used software in stochastic modeling with a global user base. He is the Vice President of the International Commission on Statistical Hydrology and team lead for the STORMS model in the UNU Sustainability Nexus Aid program. He has been recognized for his many contributions. He received AGU's 2024 Natural Hazard Early Career Award and several Best Paper Awards. Besides being featured in many highly scientific magazines, his research has been covered by over 100 news outlets, with and TV, among others. So please join me in welcoming Dr. Simon Michael Papalexiou for this morning's talk. The floor is yours.
Thank you, Grace. Grace, thank you very much for your kind introduction, and thank you very much for your invitation to present here today. It's a great opportunity. And I will start right away. I have quite a few slides. I will try to be on time. And as you said, today's talk is about simulating hydroclimatic processes and extremes with stochastic methods. So allow me a small introduction. As you know, physics is essentially our hope to understand nature. And there are many systems that are fully, actually all of the systems, governed by physical laws, but this doesn't mean that they are predictable. And a good example is the two-arm pendulum that is totally chaotic, as you can see in this animation. And on the other animation, you can see 40 pendulums starting with a very, very slight different initial position, and they end up in a very chaotic movement, totally different one from another. And, you know, if we go back in the 60s, there was this euphoria that we would be able to predict everything. And I mean, the weather and so on, because computers, it was the era that computers started to evolve rapidly. So when Lawrence was working to solve the evolution of the atmosphere using some very simple differential equation, he essentially did this rounding of a few digits, and then he went for a coffee. And when he got back, he saw this graph. he saw a very different future. And initially, he couldn't understand. This is how chaos was discovered, and this is how we realized that essentially we cannot predict much, in many cases at least. This is his famous paper. So nowadays we have really great models, global circulation models that try to simulate processes in the atmosphere, terrestrial processes, also cryosphere, oceans, and put all of these things together in order to be able to simulate the evolution of climate in Earth and other parameters. But the point is, and I leave this to our audience, can we eventually add all physics in these models? And if we do add all physics in these models, still we'll be able to converge to reality. Remember, the two-arm pendulum is a very simple system and we cannot predict it. Imagine the complexity that we have in the atmosphere. On the other hand, many of these processes, you can see a grid in the Earth, have to be simulated at very fine scales because some processes occur in very fine scales, actually. And most of the global models we have right now, are between 10 and 100 kilometers resolution. Of course, we have regional climate models at finer resolution. So there are some scale limitations here, and also there are temporal resolution limitations. For operational purposes, we might need even simulation at 5-minute scale. So imagine the computational burden, power that we need if we want to simulate at a very fine spatial scale and a very fine temporal scale. So this is why I believe also probabilistic modeling and stochastic methods are very useful, and they can facilitate a lot of operational ways. For example, as I mentioned, there are unpredictable dynamics in Earth system, chaotic system. There's a very high complexity, and all models, including deterministic models, have limitations. So it is a very long list of what probabilistic modeling can help do. So beyond enhancing the robustness of deterministic models by adding essentially uncertainty, we can simulate extremes because we have more control directly. Most of these models, not all, are data-driven models. We can generate realistic synthetic time series, as we're going to see, or even fields. They have several applications in forecasting. And of course, all of these can be used in an operational manner to support decision-making and infrastructure design. So what exactly is stochastic modeling? The way I see stochastic models is like a different kind of virtual reality. You observe something and you want to predict something similar. You generate something that didn't happen, but could have happened. For example, here you're seeing a simulation of a time series, a simulated time series using stochastic models of precipitation in Saskatoon, where I used to live a few years ago. And as I mentioned, we have more flexibility. This, for example, a simulation of discharge that we can play with the heaviness of the tail, and you can see in the last panel of this animation an extreme popping up because the tail is very heavy. Temperature have different marginal distribution, typically bell-shaped, a slight positive skewness, sometimes even negative, depending on the location. Relative humidity, as you can see, the variable is between 0 and 1, depending if you are in a wet or a dry region. The profile of the humidity can also be very different. So the question is, what properties should a model preserve or reproduce? Ideally, the perfect stochastic model should reproduce the joint distribution of any order and at any scale of the process under investigation. But the point is this feasible? If it is feasible, is it meaningful? Because there are some models that we can simulate or use a lot of parameters to try to model the joint distribution of any order. But the point is that these models become so complicated and the parameters can be so tough to estimate and so uncertain that actually doesn't have meaning. So the point here is how we can create something that is robust, easily applicable, and it has also practical applications. So what I'm saying here, and I will explain when it is not a good approximation or we can have a better approximation, is that we should target to reproduce the probability distribution of the process we're investigating, the correlation structure. I will explain all of this in detail. And most of the times, if we produce these two things, we get some decent results, and we can refine, we can build on that. So where we are in terms of extremes. This is an older study of mine. We know, for example, that most extreme precipitations have sub-exponential tails. This means that we need distributions that are not like the gamma distribution, which was the prevailing model. So we need flexibility in our modeling to capture the extremes. Another recent study verified that, but now is all over the US and using hourly precipitation. And also here, we verified that we need sub-exponential tails to do a good job in representing extremes. And these are just an example, two of my own studies, but there are numerous studies, probably thousands, verifying these results. So what I suggest, focusing on the first component of this modeling scheme, is that especially when we're describing distributions defined in the positive real axis, we should use distributions that allow some flexibility both on the left tail, we can have J-shaped distribution, and on the right tail, so we can control the heaviness of the tail. And at the same time, we should respect the natural range of values. This means that if a variable is defined between 0 and infinity, we should use distributions that correspond to this range and not set allocation parameter where we have an artificial lower limit different than 0. This system, I used extensively the Bear system, and this is a historical paper. Those of you who are interested, I suggest reading it. Bear didn't become famous like Pearson, but his system was equally beautiful. This is another system, my own. I recently introduced it last year or 2 years ago, of 6 distribution, exactly to have a repertoire of the distributions that actually can control the left and right tail and have analytical forms. But where I want to focus here for a few seconds is that when we're using distributions that have a lot of flexibility in the parameters, and I see a lot of colleagues might even using distributions with 4 parameters, we have to be very, very, very careful. This is because the flexibility in shape can end up in parameters that are actually don't have any physical meaning, or when we use them for extrapolation, we can get strange results. So if you're not sure that what you're fitting is robust and correct, maybe someone should stick to simpler solutions like 2-parameter distributions. Now, that was the first part of the modeling scheme, reproducing the marginal or using correct marginal. The other one is trying to reproduce autocorrelation. And what is that? Autocorrelation creates clustering in space and time. Here, for example, we can see if we have a time series and shift it back, we can see that high values remain high and low values remain low. So this is the effect of the autocorrelation. This is why it's so important in operations to be able to mimic and replicate it. And also here you can see storm cells, and as you can see, it's not a white noise all over the place. You have some clustering in space. Again, this is the effect of spatial correlation. How we can reproduce this correlation? Typically, for the univariate or the time series modeling, we use parametric relationships that describe the empirical correlations. Here are 3 correlation structures that I have suggested as survival function of probability distributions, and some of them have reappeared in the literature also many times, as I'm going to show. But why use a parametric autocorrelation structure and not reproduce the sample correlation, which is represented here with the dots? As you can see, we have a very high fluctuation. And this simply means that what we observe, it is not what it is. It isn't the reality. So it's better to have a parsimonious model, a simple model with a couple of parameters to describe our correlation structure. And as I mentioned, there's more than 50 years of research in using correlation structure, spatial temporal or spatiotemporal. This is an example of an old paper. I really like old papers from 1971. And here in the table, you can see many of valid spatial correlation structures. Now the point is, okay, we have our time series, we selected a marginal distribution, and we estimated a correlation structure. But how we reproduce that in a model? So the way I'm approaching this, I'm using the famous autoregressive models from Box and Jenkins. And as you can see, this model here is very simple and very beautiful, because what it says here is that what is going to happen now depends with what happened yesterday, maybe 2 days ago, 3 days ago, depending on the scale. And this is multiplied by a coefficient, so it's a linear model, plus something. I call this magic, the component epsilon in the end. And it's magic because it's a random component and incorporates all the things that we cannot predict. So we have a model that depends on the past, which makes sense. And because we wouldn't be able to predict exactly what happens, then we add a component that is random here. So the rest are technicalities, how essentially when we have fitted an autocorrelation structure, we estimate the parameters of the model, but this presentation is not technical, so I will skip these details. Now, the previous model that I've shown, it is excellent in generating Gaussian time series, meaning that the outcome will have a Gaussian distribution and a Gaussian dependence. But in reality, and in the animation I showed in the beginning, you have marginal distribution describing precipitation, discharge, humidity, wind speed, even temperature that are not Gaussian. So the point is, this model as it is wouldn't do the job. But there is no problem. We can generate a Gaussian time series. We can take the CDF, which means we transform to probabilities. And then when you have uniform probabilities, you can map back using any distribution you like, the quantile function of any distribution you want. And that would be very easy and really great, but unfortunately, is not that easy in the sense it was proven way back that whenever we apply a nonlinear transformation to a bivariate Gaussian distribution, essentially we're decreasing the correlation. So this means if I go back to this slide, if there is a correlation, let's say R in the first time series, we'll end up with something lower in the last time series because of this theorem over here. Okay, and this is the paper in, I think, in 1971, but 1957. So the idea of being able to estimate the corresponding correlation, so when we transform, we get what we want, is not new. I managed to found a thesis by Connor in 1971 in Georgia Institute of Technology. I managed to find a study from US Army Missile Command, and it seems that the first paper was published in 1975. Of course, these studies were in a very primitive and limited, let's say, operational form, but at least some of the main ideas were even there. So several years ago, when I started working with this thing, I didn't have idea of these previous papers, and this is good sometimes because you can introduce novelties. I use something called correlation transformation functions that make this job easy. So if you want, for example, you observe the red autocorrelation and you want to simulate first a Gaussian time series and transform, then you will need the blue one. And this depends also on the margin. And with these correlation transformation functions that look like this over here, we can easily plug in the estimated from the data correlation, and we can get back the Gaussian correlation, and then we can do our job. So this is a slide highlighting that this scheme is very general in the sense that we can use mappings from the Gaussian distribution that we generate with the autoregressive model that showed to any other distribution. It could be binary, as in the first panel over here. It can be any continuous, or it can be a mixed type if we want to simulate intermittent processes like precipitation, wind, or even discharge of, let's say, ephemeral and small streams. And this schema also can be extended to negative correlations, but typically for autocorrelation to be negative doesn't have a lot of practical applications. So to keep things simple and clarify all of these technicalities, which I repeat, I avoided to go in detail, is what do you have in reality? In reality, you have just an observed time series as in panel A here. So with this scheme, you just fit a distribution, any distribution you like, with any method you like, moments, and moments, maximum likelihood, least square, it doesn't matter. It's up to you. You also fit an autocorrelation, and these are representing the observations. Then for this given distribution that you have estimated and fitted, you can easily estimate the correlation transformation function. And then you use these correlation transformation functions to estimate the correlations of the autoregressive model and generate your Gaussian time series. And in the last step, you are transforming this time series using the observed distribution to get time series in the natural space, as you can see here. So this, as you can understand, is a very general scheme and you can apply it into anything. But this doesn't mean that always perform ideally, but you can get some decent results in most of the cases. But we can, let's say, specialize or refine this scheme for many cases, as I'm going to show now. For example, we can simplify the scheme to generate binary time series. As you can see here, I suggested a very simple formula. So a binary time series have a specific correlation and a specific probability of 0. So if you know the probability 0 that you want to estimate, you plug it in this little formula, you get this coefficient Cp, you plug it here, and then you have your correlation transformation function. So you can apply the scheme even in Excel. And what you can do with that, you can generate very easily, as I mentioned, binary time series. And binary time series 0, 1 are very important, simply because you can transform a lot of time series, existing time series, into 0 and 1. For example, rain doesn't rain, or I get an extreme or I don't get an extreme. So it's a useful methodology to generate this type of time series. Now let's go back and revisit a little bit the issue of intermittency. In the previous general scheme, we were generating intermittent process by mapping Gaussian values below a threshold to 0 and above this threshold to a continuous distribution. However, in a publication a couple of years ago, I showed that there is an infinite number of combinations if I multiply a binary time series, the blue one, with one that has a continuous marginal, the green one, to get actually a time series that has exactly the same marginal and exactly the same autocorrelation. So this simply means that we can refine the process if we fit first a binary time series to express wet-dry spells, and then a process to describe rainy amounts given apparently that we have rain. And not only that, this scheme can be further refined because we can use general dependence structure, general dependence expressed by copulus. And I will briefly explain that. So far, I mentioned correlation structures that essentially are the estimates of the Pearson correlation coefficient, which is just one measure of associations. We have many of them. Non-parametric, parametric, information-based, entropy-based. But the most general type of dependence is expressed by different type of copula. So we can generate continuous time series over here that have a specific dependence. And why this is important? It's important because if you see in the first case with the Clayton copula, the panel D over here, this is a dependent structure that doesn't have upper tail dependence, which simply means when you get an extreme, it is highly unlikely that you also get another extreme. But if we generate this time series with a different dependence, for example, the Gumbel dependence, you can see here in this scatter plot panel J, how it looks. If we get an extreme, it's highly likely that the next value also be extreme. So this is very crucial to be able to identify the correct dependent structure. So what is the main difference by using the mixed type distribution, let's say the general model to generate precipitation, or using this two-step by simulating separately the binary time series and then the continuous, as you can see in panel C? Because the distribution is exactly the same, but in the second case, as I mentioned, you are simulating separately the wet-dry spells and the continuous process. What is the difference? Because they look very, very similar. And actually, they are not. If we assess this simulation at the basic scale that we have simulated, actually, it looks very good for both models. But then if we start aggregating, this is a simulation at the hour scale, by the way. But then if we take our time series and aggregate at the 2 hours, 5 hours, 10 hours, 20 hours, and so on, we notice that when we simulate separately the binary process and the rainy, let's say, spell process, we get very, very accurate results through all the time scales. You can see the red line is the observed scaling, and the brownish is Cosmos 2s, 2 steps, and the other one is Cosmos 1. So we get very precise representation at all scales, which is actually great. In the past, we need to use disaggregation schemes to achieve something like that. And the performance is also much better when we investigate the extremes, the annual maximum in this case, at larger scales. And this is very important in hydrology, engineering hydrology, because having a model to be able to represent accurately maxima at different scales is, let's say, the cornerstone of hydrology, operational hydrology, and engineering hydrology, for design purposes, of course. Now, you might have now the question, and you say, okay, Simon, this is good, but there are so many studies showing that there are changes in extremes. And, would these models be able to do it? Okay, so on a quick note, indeed, there are several studies. This is one of my own a few years ago that we managed to show with a new method that indeed there are clear changes, at least in the frequency of extremes. And this is another study that spotted changes in seasonality, intensity, and duration in extremes. So the point is, given this, or if you want to simulate time series that some properties change in the future, can we use this type of stochastic models? And the answer is yes. This is from a previous study, although the main topic in this study was disaggregation, but actually in this study we showed that you can apply this modeling scheme also to generate time series that their properties change in the future. So essentially you use non-stationary time series. So this is a simulation that the mean of the rainy days change by 40% over the next period of 80 years. And the second simulations will change the mean by 30% and the standard deviation by 30%. Sorry, 40 and 30%. So we can do also that. And it's not a matter of only being able to try to simulate observed changes, but you might want to stress test a system. So you might want to create different scenarios. For example, you have a specific change in these properties for the future to see if your system can withhold these changes. Okay, and also if we want to disaggregate climate model projections in the futures, we know that these projections are non-stationary because we know they predict changes in the futures. This scheme can also be very helpful because we have applied to be able to downscale, disaggregate different projections, monthly projections, even into hourly. Okay. So this is fine. This regards the univariate simulations that are very useful in many cases, but for, I would say, more practical applications, we might need a multi-site or multivariate simulations, because in reality, in a region, you have multiple stations and you might want to simulate synthetic time series in all of these stations. So this is just an example. I'm just depicting the positions of 5 stations. And on the right is what it is known as the distance matrix. It's simply a matrix that indicates the distance between any 2 possible pairs of stations. And the whole idea here is that we're going to use these matrices. Later on, I will show you how. But we can create, instead of estimating the autocorrelation or the empirical correlation, now we create the correlation matrices, which essentially the pairwise correlation. This matrix is the lag 0 correlation and indicates the correlation between any pair of stations in the region that we're investigating. And the whole idea is that we can also transform this matrix into the Gaussian space, so we can generate Gaussian time series and transform back. And of course, these correlation matrices can represent the lag 1, lag 2, lag 3. They can go back as many lags as we like. And I repeat, the idea is exactly the same. There is, however, an important difference here. For those of you that you were very attending carefully, you will notice that the correlation transformation functions in the autocorrelation case, always they will end it up to 1, and they were concave. This is not the case when we're talking with cross correlation. For example, if one station has the distribution, the black one and the other on the blue, and we want to simulate and we observe a 0.5, then the Gaussian simulation should be 0.8. But the most impressive here is that no matter what we do, we won't be able to observe a cross correlation larger than approximately 0.55 in this case. It seems that there is an upper limit. And this is a point of caution, because sometimes we see variables and we say, okay, they have a correlation 0.5. But it seems that nature likes to hide its correlations. It is a limitation of the Pearson correlation, the linear correlation, that cannot reveal a larger correlation. So this is something to keep in mind, because 0.5, 0.4 correlation in some cases actually can be a large value if the variables under investigation have very different marginal distributions. So the difference here is that instead of using the univariate autoregressive model, we use the so-called vector autoregressive model. You can see here now Z is in bold, which means it is a vector which can represent the different locations. If you have, for example, 100 stations, this will be a vector of 100 values. And then A now are tables and not coefficients. Things here, unfortunately, get a little bit more complicated, in the sense we have a lot of boring technicalities. There are a lot of matrices that have to be inverted, and sometimes there are instabilities, numerical instabilities. So this can get a little bit more tricky. For the vector autoregressive of order 1, we have simple analytical solutions. Also for vector autoregressive of order 2, but then it gets more complicated. There are also some solutions that we can fit an autoregressive model, a vector autoregressive model of any order. So previously, I just indicated that you will need a different correlation transformation function for any pair of stations. So this scheme wasn't operational in this way if you wanted to simulate, let's say, 10,000 stations. For 1,000 stations, this means that you would have to simulate to estimate approximately 6 million different correlation transformation functions. And this, you might need to wait, I don't know, even weeks. So recently, we managed to solve these bottlenecks. We transformed all the variables in the space called mixed uniform. Again, I will skip the details, but now instead of waiting weeks, we can have this in a few minutes. And I'm gonna just show now a simulations we did with 1,000 stations. Imagine that you have 1,000 different time series in different locations, and we perform this all over the Mississippi Basin, as you can see here. So these scatter plots, density scatter plots, indicate that the simulated and observed values lie over the one-to-one diagonal, which means we are able to reproduce in all of these 1,000 stations very well probability zero, the mean value, variation, skewness, kurtosis measures, and the maxima. I repeat, this is daily precipitation. Also, these scatter plots here show that we were able to reproduce the correlation matrices. Of course, here the matrices are huge. They contain 1 million entries. But again, we were able to reproduce very decently, as you can see, both in the matrices and also in the scatter density plots, the spatial and the temporal correlations. Fine, but then the next step would be, okay, I understand the multisite, but how about fields? Because what we have in reality out there is essentially nature simulates mainly in continuous space and time. I would say probably always, most of the time. So you might want to simulate fields. Can we use this also to simulate fields? So the difference with the fields is, at least in this scheme here, it's just the sites of the station, they are on a regular grid as the one I'm showing right here. And this regular grid, of course, has its corresponding distance matrix, which is simply the distance between any 2 points in the grid. Now, the main difference here is that we typically use some constructs called spatiotemporal correlation structures. They are parametric. This is one that we introduced a few years ago. I will skip the details. It's just defined as a copula function that takes as argument survival function. So this is nothing mystical. For example, this is one we introduced, I repeat, a couple of years ago or 3 years ago. It's called the Clayton-Weibull spatiotemporal structure. It looks like that. It's just a regular bivariate expression. And what it does is it takes the distance matrix of your grid, and if you apply the distance matrix, if you apply this function for all values, all distances in the distance matrix for different lag, you transform it to correlation matrices. And now we can use these correlation matrices essentially to transform, based on the marginal we want our fields to reproduce, to the Gaussian spatiotemporal correlation structure. And then the idea is more or less exactly the same. We're generating now Gaussian fields and we're transforming them back into whatever distribution we want. Okay, but there is another piece in the puzzle, because anyone who has looked outside the window, for example, the clouds, they would observe that everything moves. And if you look radar pictures from reflectivity or storms, they also move. And this is at fine scales. So if you want to simulate storms at, let's say, 5 minutes, then clearly the previous approaches are not sufficient because the whole system moves across the region. This is called advection. And also, it's not only that. If you see pictures, radar pictures, you will see that some of the cells have a preference in specific direction. This is anisotropic. So the point is here, can we modify the previous methods to introduce also these components if we want to simulate at finer scales? And the answer is yes. Beyond the schemes, there are also other schemes that are trying to do these things. Now, from a technical perspective, this can become quite complicated. This study was published in 2021. And I will just highlight the main idea. If you have advection, the random variables on the grid points behave like they are in a different spot. So essentially, the distance matrix we're using to estimate the lag correlation is different. And if we have an anisotropy also, the lag zero correlation matrix is transformed. So the random variables behave that they belong in a different grid. And if you see the spatiotemporal correlation structure, now it becomes a little bit strange. It has some peaks in space and time, and it's not like having the highest correlation at zero distance and zero lag. And this depends solely on the velocity field. So what we did back then is that not only we were able to replicate linear velocities, as in this case, but we managed to generalize the framework to use any velocity field, and I will show some example. Here is, for example, a simulation with a field that is moving with a linear velocity without any anisotropy. If you see, the storm cells are essentially symmetric for all directions. In this simulation here, you can spot the difference. You can see that the storm cells are elongated and they are perpendicular in the movement. In reality, it's actually the opposite. The cells are elongating along the movement of the weather pattern than essentially perpendicular. So, as I highlighted, the cool thing here was that we generalized thing to have a velocity field that is not linear. If you spot in panel A here, we have some streamlines that are bended. They have a curve. Okay, so if you spot the animation very, very carefully, you will see that this system moves across these streamlines, which are not straight. And also we applied this to even different cases. As you can see here, we managed to couple a velocity field that moves toward the center, and it has also rotation. And we coupled this with a swirl anisotropy to be able to simulate cyclonic movements, and hopefully we will be able to simulate tornadoes and hurricanes at larger scales. And not only that, here is a velocity field that essentially moves from two corners in the center and escapes from the other two corners. So this is like having colliding masses of air in the center, and they have to escape from the other two corners. This is also an anisotropy. It's experimental. I'm not sure if it has any use. It's a little bit, we're just playing with these wavy anisotropies. Maybe in geological patterns, there are some of these spatial anisotropies for sure. And this is a final example. We have a positive divergence. It's like having a mass, a source in the center, and everything expands outwards toward all directions. And then the sink, negative divergence, is like having something essentially, or like you cool the air in the center and then the air moves toward the center from all directions. I will close in a couple of slides, and I want the last comment here, because this is something that we need as a community in general, as a scientific community, as practitioners, is about essentially downscaling. I mentioned that we had applied these techniques for downscaling univariate time series, but what we need really is to get pictures like that from climate models and transform them to fine scalar solution like the one over here. Can we do that with stochastic models? Yes and no. It gets complicated and it's tricky. For the univariate case, it works very nice, very easily. This is an algorithm we published a few years ago in 2018. It's called DeepMac. We can do this successfully. However, still, these are very useful. This is an example, an ongoing study. We managed to use stochastic models, couple fields to train different neural networks. And we have some really great results, especially using the WGANs in downscaling storms. You can see the aggregated fields and how well these neural networks manage to downscale them. So essentially, I'm closing. For those of you who are interested in investigating these methodologies, we have a software. We spend a lot of time to develop it. It's totally open and free in R. It has thousands of downloads by now, and hopefully over the next year, we'll update with several of the methodologies that I just presented, because currently not all of them are incorporated in this software. And these are the publications that essentially are describing the Cosmos software and the Cosmos methodologies, I would say. So yes, that's all. That's from me, and thank you very much. I hope it wasn't too technical.
Well, let me answer that for you. It is technical, but the next couple of minutes we'll try to tease out some, some practical, reality that will touch reality in it. But let me first and foremost say thank you very much for your time and the effort to really explain the abstracts, the technicalities, to everyone. But for me, the first thing that jumped out was when you were trying to talk about the Gaussian process, the distribution, and in one of the equation, you left this, the last part of it, plus summation mark in brackets T, that T, according to you, representing factors that are not predictable. Can you give me an example of such factors that you think are not predictable?
Well, I will very the question. I would say, what is actually predictable 100%? The answer is nothing. So I can give you a very good simple example. Here in Calgary today, we have like -10 or whatever. Yesterday we had, I think, -5. I think in the night it was like that. Would it be possible to have like +30 yesterday and -5 today? No, because there is some correlations. And this correlation indicates that, okay, if yesterday I had a high temperature, apparently today I will have also a bit of a high temperature. But given the knowledge that yesterday I have a specific temperature, will I be able to predict exactly the temperature of today? The answer is no. And this is the component of magic where we need to add something to allow this uncertainty and this variability in the outcome.
So what I'm getting is it creates flexibility, but at the same time, we're just still trying, So I appreciate the effort at trying to predict because it makes sense, especially for planning and all that, but how do you really I'm seeing I'm looking at how to frame this, that will make sense. How do we really, test? Is that the word? How do we really test the truth claim of this? Because they're probabilistic. It's just, probability this will happen, probability this will happen. We've tried so much to get it right and all this kind of thing. But, the chances that you don't get it right, the consequences can actually be very grave, So how do we really test the truth claims of these models, of this, scenario,
Well, I think that is the immense beauty of probabilities because it assigns a probability to any outcome. And if someone says, okay, I have a model that can predict exactly what is going to happen, they are wrong. We cannot predict exactly. And the beauty of probabilities, it allows for something else to happen. But the best thing that we can is trying to figure out where is the largest probability.
Thank you. One more thing, for me is I was having this interesting discussion not too long ago around correlation. That we scientists will like to throw, this statistical correlation at people, but generally it doesn't always translate to causation. So what's your take on that?
Oh, this is clear. I mean, the correlation is not essentially, doesn't, in many cases, it does not reflect the cause. For example, I can create a totally artificial time series right now that has a positive trend, and another one with a positive trend. They will be correlated, and they are totally independent. There isn't any cause effect, absolutely nothing. So in this case, the way that we are applying these methods, we know that there is some form of correlation. For example, it is the variable itself. We're talking about autocorrelation. It's precipitation with its previous step. It's discharge with its previous step. Apparently, there is a correlation. It's rising, recessing, and so on. Same with the temperature. Now, when you're talking about cross-correlation, you're talking about two stations that are a few kilometers away. You should expect a cross-correlation. There isn't anything there strange. But yes, you're absolutely right. Nobody can deny that. There are, in many cases, we have to be very careful when we're identifying cross-correlation between two variables. I just gave you an example. You can take any two variables, add both of them a positive trend, they will end up being correlated with a positive value, which, you know.
So I hope that to continue to drive us, to ensure, because this, I guess the bottom line for me is, at the end of the day, the effect of all this, it lands on people, and when it lands on people, you can't take that lightly. I mean, if get it all wrong, some lives will be lost, properties will be lost, people's lives. So at the end of the day, the effect is real. Despite that, we are trying all these abstract technicalities, and all that, but the end result, the end point of the race is making sure that we minimize the impact on real people like you and I. We minimize the consequences on real people, and that you cannot joke with, and all that. So I appreciate the fact that people like you are in the space, trying to just keep helping humanity, even if you don't understand all the intrigues that goes into into the behind the scene, the server, the data, and making life easier. I can understand the complexity of, from 5 stations to 1,000 stations, and all this kind of thing, and still trying to make sense, to make sure that, well, there are real lives behind those 1,000 stations. There are real people behind, a regional analysis, So at the end of the day, it comes down to people. So I want to appreciate that. I hope our audience too will appreciate the sense, the thoughts, the science, behind all this, that this is not just a game of numbers or a game of equations. The end point is trying to save lives as much as possible, more so when there's natural occurrences. The frequency of these natural occurrences is beyond what we expected, and I guess it gives us a good appreciation, of the fact that nature, it's bigger than us, and in our own little space, in whatever it is we do, we should try to keep working to ensure that things are better, for each and every one of us. So on this note, I can't see any Q&A anyway, but on this note, I want to really
just a small comment, Grace. I fully agree. It's all about people. We're not doing this just doing these things. At the end of the day, we hope, I'm hoping that I'm representing any scientist here, that we hope whatever we do at the end of the day will be applicable and make our world a little bit safer. So we can estimate the risk a little bit more accurately, and we can essentially translate that into a safer infrastructure or something like that. This is crystal clear. We're doing what we're doing because we hope that has applications in the real world, and we are helping understand the extremes and eventually helping decision making and policy translation and all of these things.
Thank you so much. I really appreciate this. So on this note, I'd like to call it a wrap. Thank you, Dr. Simon Michael Papalexiou. I really like your name.
Okay.
Or just instead of Dr. Simon, say Dr. Papalexiou. So thank you for your time. Thank you for the insight you've given us into the work you do. And we hope very soon in the near future, you'll be back here to share more thoughts on, more advances, and how this relates to humanity. So thank you very much. Bye for now.
Thank you, Grace.